Good morning. In today's session, we will learn about uh, 3 points. One is critical state, then two-phase region, and intermolecular forces. Okay, so this is the definition for critical state. A critical state can also be termed as critical point. It is the end point of a phase equilibrium curve, or it is the end point of the pressure temperature graph that designates conditions under which a liquid and its vapor can coexist. Okay, so that is the definition for critical state or critical point. So these two definitions you have to study. Now they have quoted an example. One is the liquid vapor critical point. That is, we know at high temperature gas cannot be liquefied only by applying pressure. At critical state defined by critical temperature Tc and critical pressure Pc, phase boundaries vanish. Okay, so liquid vapor critical point are an example for critical point or critical state. Another one is the liquid critical point in a mixture, and the third one is the liquid vapor critical point. So here you have to study the two definitions for critical state or critical point and examples, that is liquid vapor critical point, liquid critical point, and liquid vapor critical point. Okay. Then this is the pressure temperature diagram of a pure substance. Now we know the three common phases of matter are, which are they? Solid, liquid, and vapor. Okay, in pressure temperature diagram, as the one shown here, they are separated by phase boundaries. That is pressure temperature combination where two phases can coexist. At the triple point, what is meant by triple point? It is the point at which the three phases of matter, that is solid, liquid, and vapor, coexist in equilibrium. That is the definition for triple point. However, liquid vapor boundaries will terminate, or it will end in the end point at a particular value of critical temperature and critical pressure. This is called critical point. That is another definition. Critical point is that point of critical temperature and critical pressure at which liquid vapor boundary terminates or liquid vapor boundary ends. Okay, so you have got the definitions for critical point and triple point and examples. Now for water, critical point is about 374 degrees Celsius. And in a region near critical point, what are the peculiarities that you can observe? That is discussed in this slide. That is near critical point, the phases, that is liquid phase and vapor phase, they will look almost similar. Okay, and another peculiarity that you can see is that at critical point, some properties will be exactly the opposite. For example, under normal conditions, water is incompressible, it has low thermal expansion coefficient and has high dielectric constant and is a excellent solvent. That is the properties of water under normal conditions. But when it is observed at critical point, that is at critical point, all these properties of water will change completely. That is, you can observe the exactly the opposite properties. That is, at critical point, water will be compressible, expandable, poor dielectric, and bad solvent. See, the exactly opposite of what we have discussed about the properties of water in normal conditions. So this is a second property that you can observe at critical point. What was the first point? At critical point, there is no distinction between liquid and uh, vapor phase, and the other one is that under normal conditions, the properties that we observe in a matter at normal conditions will be exactly the opposite at critical point, and you can give the example of water there. Then the third point is that at critical point, there is only one phase can exist, that is heat of vaporization will be 0. And you can see an inflection point, see here, in this PV diagram on this constant temperature line. On the PV diagram there will be an inflection point, which means that the variation of pressure with the volume, its first derivative and second derivative, is taken as 0. And above critical point, matter exists in a state called supercritical fluid. What is supercritical fluid? Definition is here. Above critical point, there exists a state of matter that is continuously connected with both liquid and gaseous state. It is called supercritical fluid. So, at above critical point, matter exists in the supercritical fluid state. So, these are the 3 slides dealing with the critical state or critical point. So, these 3 slides are important. Okay. Hope you understand the points that you have to note. What is the definition, example, then this diagram, plus the behavior. What are the peculiarities that you can observe at a critical point, the 3 points. Okay. Another important one is the two-phase region. As the name suggests, it is nothing but a region that contains two states or two phases of substance simultaneously. So, as said before, in the pressure temperature graph that we have seen, you can see 3 curves. See, one curve actually separates between solid and liquid. This one separates between liquid and vapor, and the other, this one separates between solid and vapor. So you can see 3 lines there, or 3 curves. Okay, see, now that is one separating solid and liquid, second one separating liquid and vapor, and the third one separating vapor and liquid. So the two phase regions are, which are they? Solid liquid, liquid vapor, and solid vapor. A point on any of the 3 lines will represent any of these two phase region at a particular temperature and pressure. So the two phase regions are solid liquid, liquid vapor, solid liquid, liquid vapor, and solid vapor. Now there is one more two-phase region. It is called dense two-phase region. It is defined as a region whose pressure exceeds critical volume. Now this two-phase region, its peculiarity is that it has no definite volume or shape, and it will completely fill the container which it is placed. This, and it also contains fluids in both gas and liquid simultaneously. So this is the definition for two-phase region and some of its important features. Last one is intermolecular forces. We know that when pressure of the gas increases, definitely the molecules will be crowded together. That means its volume will decrease. But we know molecules are individual finite objects and they have volume of their own. Okay, and so this will place a lower limit on the volume into which they are squeezed. So by applying a limiting condition of zero pressure, we can express the ideal gas equation of state as limit pressure tending to 0 PV equal to nRT. Now let us discuss about the repulsive force and attractive force. Intermolecular forces means actually the forces that exist between molecules in a matter. It can be either solid, liquid, or gas. Okay, that is the definition for intermolecular force. Now this intermolecular force can be either attractive or repulsive. Now let us discuss about repulsive force. Okay, when the gas is compressed, what happens to the individual molecules? They will begin to get in each other's way. That is, there will be a decrease in volume. So when gas is compressed, there will be a decrease in volume, and so in order to oppose this decrease in volume, what happens is that the molecules will extend repulsive forces on each other. As a result, the curve on the pressure volume versus pressure graph, that particular curve, it will shift upwards as pressure increases, and this phenomenon is observed in almost all gases, especially at high pressures. Next is attractive force. When uh, the distance is very close to each other, all the molecules repel each other. Why? Because their electron clouds will come in contact. That is, when the distance between the molecules decreases, the electron cloud surrounding them will come in contact. At greater distances, there will be a brief fluctuations in the distribution of these electron clouds, and this fluctuation in electron clouds will give rise to an attractive force between all molecules. So when the distance between the molecules decreases, their electron clouds will overlap, but when the distance increases, there will be a slight variations or fluctuations in the electron cloud surrounding them. This will give rise to an attractive force between the molecules. So if the number of electrons in the molecule is higher, then the attractive force also will be higher. Now this uh, material or the matter that we consider will remain in the gaseous state as long as the thermal motion dominates attractive force. That is, as long as the thermal motion is greater than attractive force, the substance will exist in the gaseous state itself. But at low temperature, attractive force will become greater than thermal motion. So substance will change its state from gaseous state to liquid or solid state. Okay, so these are the three sessions that we have discussed today. One is critical state or critical point, then two-phase region, and finally intermolecular forces. Okay, in the next class we will discuss about Van der Waals equation of state. Okay, for today this is enough. Thank you.